Imagine a global logistics CEO waking up to a severe, unstructured crisis. Overnight, global fuel costs have spiked by 15%. The immediate dilemma is a tightrope walk. The executive has to adjust operations and pricing immediately to protect their profit margins, but they have to do it without bankrupting the company's operational budget or alienating their loyal customer base with sudden, massive price hikes. Traditional operational databases, systems built for online transaction processing, are essentially useless for solving this specific problem. They excel at recording yesterday's completed deliveries and processing single-row transactions, but they are entirely passive systems. They log exactly what happened, but they cannot predict what to do tomorrow. At this scale, human intuition and basic spreadsheets also fail. A global supply chain contains millions of moving variables, shifting weather patterns, changing driver shifts, strict warehouse capacities, and fluctuating tariffs. Attempting to manually calculate the exact ripple effect of a sudden fuel spike across that web is impossible. To navigate this, modern executives rely on a decision support system, or DSS. A DSS is an interactive, computer-based information architecture built specifically to evaluate complex, semi-structured, or completely unstructured business problems. To bridge the gap between raw historical records and forward-looking strategy, a DSS is constructed from 4 distinct, highly synchronized subsystems. The first piece of the architecture is the data management subsystem. Before a computer can simulate the future, it needs a clean, highly structured anchor to the past. This animated flow diagram illustrates how the system operates. It connects directly to the enterprise data warehouse to pull specific, integrated historical records, extracting years of past fuel costs, seasonal profit margins, and specific delivery route efficiencies into the central processing hub. Once the historical data is staged, it enters the second component, the model management subsystem. This is the mathematical brain of the operation. It contains an engine of financial and statistical models. The system takes those historical baselines and injects the new 15% fuel spike variable. It then applies complex regression and linear programming algorithms to calculate the exact multi-layered ripple effects across the entire supply chain. The data management subsystem provides the baseline reality, while the model management subsystem provides the computational power to actually run the what-if simulation. But applying pure mathematics to a business problem is dangerous. A statistical model focused only on efficiency might suggest a theoretically optimal but practically impossible solution, like routing heavy cargo trucks through an unnavigable, snowy mountain pass just to save fuel miles. As we look at this logic flowchart, we see the third component at work, the knowledge management subsystem. This acts as a strict filter gate. It is an intelligent layer containing domain-specific rules, legal constraints, and business heuristics. These built-in guardrails evaluate the math and block the impractical solutions, ensuring the simulation remains grounded in physical reality and actual business logic. The final component is the user interface subsystem. The logistics CEO is a corporate strategist, not a data scientist. Staring at raw linear programming code offers them no value. This generated dashboard illustrates how the UI translates complex back-end modeling into highly visual, interactive tools. It allows the executive to use sliding scales to manipulate variables in real time and instantly see the projected outcomes mapped out on charts. A system capable of millions of calculations per second is only as effective as the interface that allows a human to seamlessly interact with it. Returning to our morning crisis, the CEO sits at this dashboard and formally runs the 15% fuel cost simulation. The system processes the variables and generates a targeted strategy. It outputs the exact route consolidations needed in Europe and the precise fractional pricing adjustments required in North America to survive the financial quarter intact. It is crucial to note that the decision support system does not execute these changes. It does not make the decision for the executive. Its entire purpose is to extract actionable patterns from massive datasets to supplement human judgment. By utilizing this architecture, the executive replaces dangerous guesswork and raw intuition with objective, data-driven simulation. In modern business, a massive archive of historical data is no longer enough to win. True competitive advantage belongs to the company with the architecture required to accurately simulate the future.